An exponential function is one of the form f of x is equal to b to the power x. So this is called an exponential function with base b. Now, first of all, it's important to wrap your head around what's variable and what's constant. Of course, the base here is the fixed constant, right? So the base is constant. So that's different than a power function. The power function, the base is the variable. Here, the variable is the exponent, whereas in a power function, the exponent is the constant. So the exponent is the variable. The exponent is the variable. Now, we know a lot about exponents and about when exponents exist and don't exist. We've studied it at depth. The main thing is, if b is negative, things are a real pain. So if b is negative, I got problems because raising negatives to things like the power of half is like taking the square root of a negative, which doesn't make sense, not in the world of real numbers. So for exponential functions, we are completely and utterly going to restrict to the case where b is strictly positive. So we're only doing this basically because powers of negatives are a problem. So negative bases are problematic. We run into all sorts of terrible issues. For example, e.g., like I said, if the base was -1, raising it to a half is fine, but raising it to a third, well, raising it to a half is bad because it'd be a square root, but raising it to a third would be fine because a cube root makes sense. That's a nightmare. It would mean that the domain is mind-blowingly confusing because only very specific values of x will work. So we just don't want to avoid, well, we want to avoid all these problems. So an exponential function is one of this form. So the base is constant and the variable is the exponent. So not to be confused with the power function where it's the other way around. So what I want to do is just go through the general properties. There's not a huge amount to say about these functions. They're extremely important for applications throughout all the sciences, so it's important you understand their basic behavior. We're going to look at kind of the most basic stuff about them. So here are some general properties. General properties of f of x is equal to b to the x. So let's divide into three cases, I think, right? First case, very uninteresting. It's not really that exponentially when you think about it. If b is equal to 1, well, this is kind of exactly the same as the situation with the power function where the exponent was 0, albeit for different reasons. Here, the graph is incredibly boring because of the fact 1 to any power is equal to 1. This is one of our kind of special case properties when we studied exponents. So super uninteresting. It's just a flat horizontal graph. So this is y is equal to 1 to the x, which is equal to 1. So it's not an interesting function. Absolutely not. So let's really not focus on that. Much more interesting is when it's greater than 1 or less than 1, of course still greater than 0. So let's look at these kind of two cases. So b greater than 1, let's think about this one first. So let's think about the graph. So the graph of exponentials is very distinctive if b is strictly greater than 1. It's something I'm sure you've seen before. xy. So I'm going to draw a few in this one thing. So imagine if I was to draw y is equal to 2 to the x. Well, if I'd never done this before, something that would be worth trying, and this is incredibly crude, would be just to choose a few values and see what happens. So for example, 2 to the 0 is 1. So I know I would have to pass through the position 1 here. So I'm thinking about y is equal to 2 to the x. Sorry. If I put in x is equal to 1, I would get 2, so it'd be a bit higher. Next, it would be squared, 2 to the 4, so 2 to the 3, 2 to the 4, sorry, which is 2 to the 2, which is 4. And it'd be getting bigger and bigger and bigger. So what's true is you get larger and larger. You get really steep really fast. And in the negative direction, what happens is, well, you have something like a half at -1, then a quarter at -2. So what happens is, in the negative direction, you get closer and closer to 0 like this. ... So that is the basic shape, if you want, of all exponential functions if the base is strictly bigger than 1, roughly. Now, let me talk about if I move around a little bit. So, for example, if instead of the base being 2, it was 3, well, what happens then is you're smaller before you get to 1, but then at 1, you're the same. So I'm drawing here y is equal to, let's say, 3 to the x. But then after, you grow faster, like that. But you still got the same kind of shape. On the other hand, if you were less than 2, but still bigger than 1, so let's say something like y is equal to 3 over 2 x, that. Well, then you're bigger before 1, and then you do grow, of course, but you grow a bit more slowly. But you still grow. So that is the basic shape of exponential functions if your base is greater than 1. Okay, and if you've heard of exponential growth, this is normally what it talks about, a function which grows in this manner. Now, if b is less than 1, it's actually very closely related, as we'll see in a second. And I'll just do one specific example. So if b is less than 1, let's kind of do the following. Notice everything's positive. That's the reason I'm not bothering with a kind of a big x. So in this case, let's do y is equal to, in fact, let's do it. Let's do y is equal to, it's a bit too difficult to see, isn't it? So we'll do it in the same color. So imagine y is equal to, I don't know, half to the x, yeah? So what would that look like? Well, let's take a moment to think about this. Y is equal to half x, that's equal to 2 to the -1 to the power x. Well, that's equal to 2 to the minus x. So that means I'm graphing 2, and instead of having an x on top, I've got a minus x. But I know what transformation it is when I replace the input with minus the input, x to minus x. It's a reflection in the y-axis. So that means this graph is going to be the reflection of the blue graph on the left. So it's going to look like this. ... Okay, so this is just 1 again. So this is the reflection of, so let's get it right. So this is just laws of exponents now, or properties of exponents. And now this is just the reflection of y is equal to 2x in the y-axis. So if I was to graph y is equal to 2x on this, it would look like this from the other side, if you want. And you could do the same thing with all the other ones, okay? If I was graphing y to a third, so y is equal to a third to the power x, that would be 3 to the minus x, so it would be the reflection of the green. Same deal if I was doing y is equal to 2 over 3 to the power x, that would be the reflection of the magenta. So nice. This is what the graphs look like. They're pretty uniform. It's not like rational functions where there's a huge amount of variation. These are the two options, basically. And from these, we can just immediately read off tons of different stuff. It's maybe worth saying something here to those people who have done calculus before, perhaps, and have something jogging in your mind about kind of important bases. When you do calculus, it turns out there's a base for an exponential function which is really important, and it's a number that turns out to be between 2 and 3, and it's a bit of a mysterious number, and it's often called e. So e is like kind of pi It's a symbol for a specific number, and it's something you study in calculus, and it's chosen for very specific reasons that I'm not going to get into. But really what we want to understand is the broad concept of an exponential function. So we're thinking about all possible bases. So in calculus, you really overwhelmingly focus on one specific base that you're going to see, but we want to kind of get a general picture. That's the reason I'm kind of doing this for all possibles. So let's separate these into two groups as usual. So these graphs basically tell us everything. What I'm going to write down is going to be a summary of these graphs, really. So first off, the domains. Both cases, because the exponent or the base is strictly greater than 0, everything works. So next, range, same for both of them. It's everything strictly greater than 0. So not inclusive of 0. You never ever touch the x-axis. In particular, in both cases, exponentials are never 0. Very important to understand. So never. So exponential functions are never 0. And I should also maybe say they're always bounded below by 0. True of both of them. Next, what have we got? Well, increasing, decreasing. Pretty obviously, the first case is increasing, the second case is decreasing. So it's truly increasing. It's increasing on the entire domain, visibly. And of course, this is decreasing. Not on some specific interval, it's in the whole thing. We've already talked about bounded below. And zeros, maybe odd and even, neither. Visibly, neither of these situations has either the symmetries we're looking for. So neither odd nor even. And finally, I'll say something about the inverses or the one-to-oneness. And even though this is really going to be the next video, I think I'm going to just point it out. They're both one-to-one. So if you're one-to-one, you have an inverse. The inverse is the logarithm function in base b, as we're going to look at in the next video. It's exactly the same on this side. Okay, so just to recap, exponential function of the form b to the x, where the base is constant and the exponent is varying. So the other way around than a power function, very important. We exclusively look at exponential functions where the base is strictly greater than 0, because we'd have horrible problems if it was negative. And then we just look at the different possibilities. So b is 1 is very interesting because it's just a flat line. So the output is always 1, it's a constant function. B is greater than 1, you're increasing. B is strictly less than 1, you are decreasing. Very similar though, you're only reflected in the y-axis. And then everything else basically follows from these pretty reasonably. And the one-to-oneness is true, basically for obvious reasons here. You can see if I give you any horizontal line, it only crosses the graph once or not at all. So I think this was an example we saw when we were thinking about the horizontal line test. So same kind of deal. So exponential functions, incredibly important in applications and throughout all of mathematics.